In this lesson, we'll continue with our study of the definite integral, denoted by this symbol here, and let's just go over what that definition is. Here I have a graph of y is equal to f of x, and I can use that to walk through each part of the definition. So the way it works is you have a lower bound a and an upper bound b, so a place where you start and stop the area. We take this region and we divide it into n equal pieces, and we call that delta x, the length of the interval divided by the number of rectangles that we're using. So this will split the interval up into a bunch of pieces, and we call these locations, these x values here, we call these sample points. So we could call this x value x1, x2, x3, and so on. Eventually you get to what we could call the ith term, so we could call this x sub I. And with this notation, you can come up with a formula for how you can count from a to end up at x sub I. You count by the number of rectangles that you have, and each has a length of delta x. So the formula for x sub I is equal to the starting point plus the number of times you're counting by delta x. So if you want to get to the ith one, you'd count by delta x that number of times. The process of actually computing this integral is called integration. So that is the process of solving a definite integral. And when you've completed this process, you could say that you've integrated the function f of x. So we'd say we integrated f of x, meaning we found its area. Let's state the actual definition that you use to do the process of integration to actually integrate the function f of x. It is the limit, as n approaches infinity, of the sum of I going from 1 to n of f of x sub I times delta x. So this part of the definition is find the area of the rectangle at each of these locations. This says you add those areas up. And then if you take the limit as n goes to infinity, you get a better and better approximation until you eventually end up at the exact value of the area. So because you can call this the Riemann integral, it's interchangeable with us saying the definite integral. This part of the definition here, just the part with the sum, is sometimes referred to as the Riemann sum. It's the part of the Riemann integral that you can use to approximate the area before you actually compute the limit. And one other term before moving on. If this value exists, we say that f is integrable on the interval from a to b. So I'll just note that if this value exists, meaning you compute it and you get a number, we say f, the function, is integrable on the interval from a to b. So in this lesson, what we'll do is we'll do a couple more computations using this definition, and then we'll examine some properties, some geometric properties that this integral has. In example 1, we have two limits of sums. Can we re-express these as definite integrals? And again, this is going back to the definition of, okay, it's the integral from a to b of f of x dx, which is equal to the limit as n approaches infinity of the sum of I going from 1 to n of f of x sub I times delta x. If we have something that looks like this, can we transform it so it looks like this, a definite integral? If we look at this first one here, I see that we're working on the interval from 2 to 5. That's going to be the lower and upper bound of the definite integral. So for this one here, we can say we're integrating from 2 to 5. Next, we have to know what function we're actually integrating, and that can be determined by this part here. So what is the function f of x that we are using? Well, here we have x sub I and here we have x sub I. That's the placeholder for x, so we can write that as x times the natural log of 1 plus x to the 4th. So this is the function that we're integrating, f of x, and that can go right here. So I'll put x, the natural log of 1 plus x to the 4th, and then we multiply by dx. So here is the definite integral that's represented by this limit of this Riemann sum. Let's try that again down here. Here the interval is from pi to 3 pi, so the lower bound a is pi and the upper bound b is 3 pi. So I can say, all right, well, this is the integral from pi to 3 pi. And now we have to look at this expression and determine, well, what function are we talking about here? I'm noticing that in this problem, the subscripts were both i's, and here this is I minus 1. In this problem here, since the sum is going from 1 to n and we're using x sub I, this means we're using right endpoints, which matches up with this definition here. You can actually use left endpoints, points in the middle, any point that falls within the interval. So down here, this is the Riemann sum, but using left endpoints of the interval. So we can really treat x sub I minus 1 and x sub I as the same thing. So what's the function that we're working with? It is still cosine of x divided by x. So it makes no difference that this is x sub I minus 1 and this is x sub I. This means we're using right endpoints. This means we're using left endpoints, but it still results in a similar function because these two things are the same. So that means we'll put that function right here. That is cosine of x over x dx. Note to actually solve this integral with what we know, we'd have to evaluate this sum and then take the limit of it. That would be very complicated, so we won't do that here. We're simply just writing the sums and limits as definite integrals. In example 2, let's go the other way in this process. Here we have a definite integral. Can we express this as a limit of Riemann sums? And here we're going to use right endpoints as our sample points. So looking at this definite integral, I first can see that the interval that we're working on is from 3 to 6. And the function that we are integrating is x squared plus 1 over x. So to write this as a limit, this will be the limit as n approaches infinity of a sum of I going from 1 to n of some expression that goes here. And that expression is going to be f of x sub I times delta x. If we use x sub I, we're talking about the right endpoints of each interval. So let's figure out what x sub I is equal to. Well, first we need to know delta x. That's the length of the interval divided by n, which in this case is 3 over n. X sub I is the starting point of the interval, which is 3, and we're adding I times 3 over n to that, which is 3 plus, I'll put 3i over n. This is what I want to put into this function in place of x, and then I'll multiply that whole thing by delta x. I think it's going to be a giant mess, but it'll look like this. It is the limit as n approaches infinity of the sum of I going from 1 to n of, okay, the function is x squared. That's 3 plus 3i over n squared plus 1 over x sub I, which is 1 divided by 3 plus 3i over n. And this whole thing is multiplied by delta x, which is 3 over n. If our goal was to evaluate this definite integral, we would do this. We would try to compute this sum here. And this looks quite challenging, but that's not the point of this question. I don't want to evaluate it. I just want to set it up to see what it would look like. Now, how would I set this thing up, this sum over here, if I wanted to use left endpoints as the sample points instead of right endpoints? And this is a very simple fix. If we're using the right endpoints, you're going to use x sub I, because our sum starts at x sub 1, which was the first right endpoint. If you want to use left endpoints, one way to do this is to use x sub I minus 1 if your sum starts at 1. X sub I minus 1 is defined as the starting point 3 plus I minus 1 times 3 over n. So to get to the answer here, we can look at every single I that appears in the sum and replace it with an I minus 1. So to get to our answer here with left endpoints, it's the limit as n approaches infinity of the sum of I going from 1 to n of, okay, we have 3 plus 3 times I minus 1 over n squared plus 1 over 3 plus 3 times I minus 1 over n, and that whole thing times 3 over n. Here, your sum, since we're starting at 1 and ending at n, it's going to start 1 earlier than up here. Here, if you put 1 in place of I, you get 0, versus up here, where if you put 1 in place of I, you get 1. In example 3, I want to evaluate the Riemann sum for the function f of x is equal to 2 minus x on the interval from 2 to 10. And we'll do this using 4 subintervals and left endpoints as the sample points. All right, there's a lot going on here. But this says we want n is equal to 4 subintervals, and the Riemann sum would be L sub 4. First, we need to know delta x. That's the length of each subinterval. That's 10 minus 2 divided by the number of intervals that we have. So that is going to be 8 over 4, and that is 2. This makes sense. If you're starting at 2 and ending at 10, and you want 4 equal rectangles, you're going to go from 2 to 4, from 4 to 6, from 6 to 8, and then 8 to 10. Each subinterval has length 2. Since we're using left endpoints for each interval, we're always going to use the left endpoint to get the height of the rectangle. All right, let's compute L sub 4. The first rectangle that we have is, this is the base, which is 2, and the height we get by putting the left endpoint 2 into the function f. So this is the base of the rectangle times the height, which is 2 minus 2. And as I can see, that is 0. To that, I'm going to add on the area of the next rectangle. The base is 2, and the height is going to be negative 2. So this is the area. Down here, I'd write that as the base is 2, and the height is going to be 2 minus 4. To that, I move on to the next one. Okay, on this interval, the base is 2, and now the height is going to be negative 3. And that's because we're putting 6 into the function to get this area. So that is 2 times 2 minus 6. And then for the last one, again, the base is 2. The height is going to be negative 6. We're using left endpoints, and that's the area of the last one. So this is 2 times 2 minus 8. I'll take these products and add it all together, and let's see what we get. All right, so I'm getting out my calculator, and the first one here is going to be 0 plus negative 2 times 2 is negative 4, plus, okay, that's going to be 2 times negative 4, that's negative 8, and then we have 2 times negative 6, that's negative 12. This whole thing, I don't really need my calculator, is going to sum to negative 24. This is kind of strange. This L4 estimates the area trapped by the x-axis and the function itself, and we're getting a negative number. But area shouldn't be negative. This brings us to a very important property of the definite integral. The way we define the area of each rectangle is by using the height of the function. Well, if the function goes below the x-axis, you're going to get negative values for these areas. And that is a completely acceptable convention. And I'm going to note this as an important fact. Area below the x-axis is negative. It'll be a negative value. So in general, area is a positive number, but when we're talking about the definite integral or the Riemann integral, the way we define it, if your function goes below the x-axis, the area will be negative for that region. In example 4, let's estimate this definite integral by using 4 subintervals and right endpoints as sample points. So here's the function x squared minus x from 0 to 2, And our first goal is to estimate this definite integral by using r sub 4. That means we're using n is equal to 4 rectangles. We need to know delta x. That's the length of the interval divided by the number of rectangles, and that's equal to a half. So to get r sub 4, I'm going to take the interval from 0 to 2 and split it into 4 equal parts. And therefore, our x values are 0, a half, 1, and 3 halves. The thing to notice about this function is sometimes the area is below the x-axis and other times it's above. For this reason, when we compute this estimate, we are really finding a net area. That's because anything below is negative added to anything to the top that's positive. So it kind of balances the amount of net area that we have over this axis. To figure out r sub 4, on this first interval, I'm going to use this right endpoint, and the rectangle that we have is this. That's going to have a negative value, and the reason is the base is 1/2, but the height is determined by putting 1/2 into the function. And that's going to give us a negative number. For the next rectangle, the base is a half, but if we put 1, the right endpoint, we're actually going to get an area of 0. And that's because we have in the function 1 squared minus 1, and that certainly is going to be 0 when we're done. Okay, for the next one, we're going to use 3 halves as the right endpoint. So it's going to be 3 halves squared minus 3 halves. That's this area here. And then lastly, we're going to have the base of a half and a height of 2 when put into this function. We get 2 squared minus 2. Now, if we simplify all this, it should represent a net area of this function. There is more above than there is below, so the answer should turn out to be a positive number. I'll compute that by putting all these values into my calculator. The value I got was 1.25. So this amount actually subtracted some of the positive value away, and this is what the net area is as we go from 0 to 2. Now let's compute this definite integral exactly. So that is, can we compute the definite integral from 0 to 2 of x squared minus x dx? Delta x in this case is going to be the length of the interval divided by n rectangles, which is 2 over n. And x sub I is going to be the starting point, which is 0 plus I times 2 over n. And that is 2I over n. The limit definition is the limit, as n approaches infinity, of the sum of I going from 1 to n of the function, which is x squared minus x, times delta x. I'm going to put this in place of both of these x's. So we get 2I over n squared minus 2I over n, and this is multiplied by 2 over n. This is the function evaluated at x sub I times delta x. I'll square this, I'll distribute in the 2 over n, and we'll go from there. This is the limit, as n goes to infinity, of the sum of I going from 1 to n of, that's 4I squared over n squared minus 2I over n. And on the next slide, I will distribute this 2 over n to both terms. So we have the limit, as n approaches infinity, the sum of I going from 1 to n of, we should have 8I squared over n cubed minus 4I over n squared. We can split the sum. This is the limit as n goes to infinity of, well, this is the sum of I going from 1 to n of 8I squared over n cubed minus the sum of I going from 1 to n of 4I over n squared. We can factor out anything that is independent of I, meaning a constant. So this is 8 over n cubed times the sum of I going from 1 to n of I squared minus 4 over n squared times the sum of I going from 1 to n of just I. We now have formulas for this thing and this thing, and they only depend on n, so I'll replace those. This is the limit as n goes to infinity of, all right, we have 8 over n cubed. For the I squared, it's going to be n plus 1, and then 2n plus 1. And that's all divided by 6, minus 4 over n squared times n plus 1 all over 2. The approach I used was to divide this n cubed evenly into these three terms, and then divide n squared evenly into those two terms, swapping the location of 6 and n cubed, as well as 2 and n squared. That looks like this. The limit as n goes to infinity of 8 over 6, n over n plus 1 over n, and 2n plus 1 over n, everything here multiplied together, minus 4 over 2 times n over n times n plus 1 over n. I'll note that this goes to 1, this goes to 1, but this goes to 2, and this goes to 1, and this goes to 1. We can determine that just by looking at the coefficients of the highest powered n terms. 1 over 1 is 1, 1 over 1 is 1, and 2 over 1 goes to 2. So this whole thing is going to be 8 over 6 times 2. I'll put that over here. 8 over 6 times 2 plus 4 over 2, which is 2. That's 8 thirds plus 2, and 2 is 6 thirds. That's 14 thirds. So that's a positive number. The area that was below the x-axis was negative. The stuff above the x-axis was positive. There was more area above the axis than was below. In example 5, we will evaluate this definite integral not by using the limit definition, but by recognizing a geometric figure. Here I have the function the square root of 4 minus x squared. And if you were to graph this thing, you would see a figure that looked like this. Starts at -2, ends at +2, and it appears to be a circular shape, but only above the x-axis, only positive. This thing actually is the equation of a semicircle. And why is this the case? If you square both sides, you get 4 minus x squared is equal to y squared. If you add x squared to the other side, you get x squared plus y squared is equal to 4. And the general equation of a circle centered at the origin is x squared plus y squared is equal to r squared, where the center is at 0, 0, and r is the radius. So when I look at this problem here, I see, oh, well, the radius must be equal to 2, and the center must be at 0, 0. And that's exactly what's going on in this picture. The center is at 0, 0. The radius is 2, because we're going from -2 to +2. But the reason we don't get the lower half of the circle is because there's no plus or minus over here. If you take this thing and solve for y, there would be a plus or minus. The minus would give you the lower half of the circle, and the positive solution would give you the upper half. So how do we solve this definite integral? It's this function from -2 to +2. What's the formula for the area of an entire circle? It's pi r squared. And we want only half of that area. So the answer to this thing is going to be, okay, well, the radius is equal to 2, so I'll take half of pi r squared. So this is pi 2 squared over 2. 2 squared is 4, 4 over 2 is 2, and the answer here is 2 pi. Same idea for this question. What is the definite integral from 1 to 4 of the absolute value of 2x minus 4? Again, we should be able to solve this by looking at a graph of the function. If you graph the absolute value of 2x minus 4, it's equal to 0 at 2, so it equals 0 here. And I know it's going to be a V-shaped graph. I just need to know what's it equal to at 1, and what is it equal to at 4, so I can complete the graph. At 1, it's the absolute value of 2 minus 4. So here, it's going to be the absolute value of -2, which is +2. At 4, If you put 4 here, you get 8. 8 minus 4 is 4, and the absolute value of 4 is 4. The definite integral is going to be this area. It starts here, it ends here, it's below the function and above the x-axis. It turns out that this is going to be the area of two triangles. So I'm going to figure out the area of the first. It's going to be 1/2 the base, which is 1, and the height, which is 2. So this entire area is just equal to 1. Over here, the area, again, it's a triangle. It's 1/2 the base, which is 2, and the height, which is 4. And this area is equal to 4. That means this definite integral is the sum of these two areas, 1 and 4. So this whole thing is going to be 1 plus 4, and that's equal to 5. In part C, we have the definite integral of the function g of x from 0. There's a 2 here. I meant to actually put a 5. So really I wanted to look at this thing from 0 to 5. You could look at it just from 0 to 2. That would be okay. I think it's a more interesting example if my function g of x is considered over this interval here. So to figure out the answer to this definite integral, I need to know this area and this area. And I think we can break this up into several pieces. For example, this first part here, it appears to be a circle. So let's actually assume that this is a circle. What is the radius of this circle? Well, the radius appears to be 1. Now we're only considering half of this circle. So if we want the area of that region, it's going to be the area of this circle divided by 2. So pi 1 squared over 2 is simply pi over 2. That's the area of that first region. Now over here, we could break this up into two pieces as well. We could say, well, first we have this triangular region, and then we have a rectangular region. So here, it's a triangle, so the area is going to be 1/2 the base, which is 2, and the height, which is also 2. So the area for this part is 2. And the last thing we have here is, well, this is the area of a rectangle, which is a base times a height. The base is 1, the height is 2, and the area of that region is 2. So we have pi over 2, 2, and 2. What does this mean about the area of the value of the definite integral? Is it simply the sum of these three numbers? And the answer is no. Anything that is below the x-axis should be treated as a negative value. So when putting these together to get the answer to this, I'm going to put a negative in front of pi over 2. The other two values are positive because they're above the x-axis, and so we have this. I would simplify the answer as 4 minus pi over 2, and that would be the exact value. The last thing I'd like to talk about for this section is some properties that the definite integral has. And again, here I've included the definition as a limit of sums. Let's say you had a constant here next to the function. We saw that with sums, you can factor out a constant and put it here. And in fact, you can also factor constants out of the limit entirely. So this thing here, you can actually say is equal to the constant times the integral from a to b of f of x dx. So said another way, if you see a constant that's in a definite integral, you can factor it out, just like we did for derivatives, limits, and also sums. What about this second property? What if you didn't just have a single function in here, but there was a sum or difference of two functions? You can split a sum up across a sum or a difference. And the same thing goes for a limit. If you take the limit of two functions, you can look at their limits individually, provided that they exist. If you put this all together, you can say that if you're adding or subtracting two functions within a definite integral, you can do them separately like this. You can say, well, we'll look at the definite integral of the first function plus or minus the definite integral of the second function, g of x. So with derivatives, sums, and also integrals, you can remove constants. You can, for them, also split them up into sums and differences. Property 3 is a combination of these two ideas. If you see a sum or a difference with a definite integral, you can split it up. If there are then constants remaining within those integrals, you can factor them out. And for this reason, this is equal to, it's the same thing as c times the integral from a to b of f of x dx plus or minus some number d times the integral from a to b of g of x dx. In this last property, notice that the a and the b are switched. Now b is the lower bound and a is the upper bound. Will that have any effect on the answer to the definite integral? And it turns out the answer is yes. What is this equal to? If you put the bounds back as normal, these two things actually are not equal. They differ by a negative. The reason for that is the definition of delta x. We defined it as b minus a over n. The upper bound minus the lower bound over n. But here, I've reversed it. Here, in that first integral, delta x is a minus b over n. And here, you can rewrite the numerator by factoring out a negative. That's negative b minus a over n. For this reason, if you reverse the bounds, a negative will come out, which you can completely factor out of the sum and the limit. So if you switch the bounds of integration on a definite integral, it will produce a negative in your answer over here. Let's use these properties in example 6. Suppose we're given that this definite integral is 10, and this one is equal to negative 2. Notice that the bounds of integration are the same. They both go from 0 to 5. Can we use this to compute this definite integral? Well, here we have a sum of two integrals which we can break apart, and then here I have two constants which I can factor out. Based off of property 3, this is equal to 7 times the definite integral from 0 to 5 of f of x plus 3 times the definite integral from 0 to 5 of g of x. Because we broke apart the sum and then factored out the constants, we are left with this part and this part. And we're actually told what those values are equal to. So we can plug in numbers for both of those things. This is 7 times 10 plus 3 times negative 2. That is 70 minus 6, which is 64. In part B, can we evaluate the definite integral from 5 to 0 of f of x? Well, this is really similar to this, but the only difference is this is 0 to 5, and this is 5 to 0. Using property 4 from the previous slide, this integral is equal to the negative of this integral. And since we know this integral is equal to 10, the answer here is going to be negative 10. So if this one's positive 10, and you switch the bounds of integration, the answer becomes the negative of it. What about this one? The integral from 5 to 0 of, well, this isn't exactly the same. It's 5g of x. So this thing here. If I look at this, so we start with the integral from 5 to 0 of 5g of x. We could first factor out the 5. That was the very first property. And then the next thing we can do is switch the bounds of integration from 0 to 5. However, if we do that, that is the negative of what we have here. Now this thing is equal to negative 2, and it's being multiplied by a negative 1. This is 5 times positive 2, and the answer turns out to be positive 10. Let's look at two final properties of the definite integral. Here, these are best understood by looking at a geometric picture of what the definite integrals represent. Let's look at this first one here. The definite integral of the same function, which is represented here in blue. The first one says, let's integrate from a to b. And the second one says, let's start at b and integrate to some spot c. So the first integral is this area. And the second integral is this area. Can we simplify this down into a single definite integral? And the answer is yes. If you add these two areas together, that's the same thing as looking at the area from A all the way to C. So if these bounds here, if this upper bound matches this lower bound, we can say this is the integral simply from A to C of the function f of x dx. This only works if you're not skipping over any area. For this final property, what happens if we integrate this function but just at a single spot? I know I put A here, but just so we don't have the same picture, maybe I'll put A over here. Like, what happens if you try to compute area under a function and your lower and upper bound are the same? What's the area of this region? And the answer is, it's nothing. The only way that you can get area under a function is if you actually have some positive distance, which we don't. So if your bounds are the same, well, that just means the value of the definite integral is 0. Let's apply these properties in example 7. So let's evaluate this definite integral. This function's really complicated, but the good news is the bounds are the same. Our starting and stopping point for collecting area are equal. That is enough to say the answer to this is simply 0. There's nothing else to do. Let's see, in part B, given this information here, can we evaluate the integral from 1 to 14 of some function f of x? Here we're told if we start at 1 and go to 10, we get an area of 8. And if we pick up at 10 and go to 14, well, then we get 4 more. These two, if we look at the integrals, this upper bound matches with this lower bound. Based on the property from the previous slide, if you integrate from 1 to 10, and then add the definite integral from 10 to 14, this is no different than integrating from 1 to 14. It's the same thing. And, well, I know this one's equal to 8 and this one's equal to 4, so this is going to be equal to 8 plus 4. And that answer is 12. And now for part C. I'm seeing that the functions are different. This is a mistake on my part. I want all of these to be the function g. Okay, the goal is to figure out this definite integral, and here we're given the definite integral from 3 to 20, and then from 0 to 20. How could I use this information to figure out this? This feels like using this property, but maybe just a little bit backwards. Let me try to think about this on a number line. If you look at this first integral, you're going from -3 to 20, and that's giving you some area. But this one goes from 0 to 20, so the other one goes from here to here. And we want to figure out, well, what's this leftover part? Like, what's this leftover area? Well, if you know the area from here to here, and that's equal to 100, and you subtract off the area from here to here, that means this stuff is going to be left over. For this reason, we can say the definite integral from -3 to 0 of our function g of x, that should be equal to the integral from -3 to 20 of g of x dx minus the integral from 0 to 20 of g of x dx. The first one's 100. The second one is 50, meaning the net result is 50. Although this doesn't quite look like the property that we used in the previous slide, notice that if you take this number and you add it to this side of the equation, your upper bound and lower bound will match, and it will equal this thing here. So you're allowed to use this property and subtract terms from one side or the other. Now, we just figured out this was equal to 50, but that's not the answer we're looking for here. I think there's one more step to do. If you want to figure this definite integral out, it's equal to the negative of this definite integral. And that means this is equal to -50, and that's the answer to this part.